In the previous video, we talked about the photo OCR pipeline and how that works, in which we would take an image and pass the image through a sequence of machine learning components in order to try to read the text that appears in an image. In this video, I'd like to tell you a bit more about how the individual components of the photo OCR pipeline works. In particular, most of this video will center around a discussion of what's called a sliding windows classifier. The first stage of the photo OCR pipeline was text detection, where we would look at an image like this and try to find the regions of text that appear in this image. Text detection is an unusual problem in computer vision because depending on the length of the text you're trying to find, these rectangles that you're trying to find can have different aspect ratios. So in order to talk about detecting things in images, let's start with a simpler example of pedestrian detection, and we'll then later go back to apply the ideas that were developed in pedestrian detection and apply them to text detection. So in pedestrian detection, you want to take an image that looks like this and find the individual pedestrians that appear in the image. So there's one pedestrian that we found, there's a second one, a third one, a fourth one, a fifth one, and a sixth one. And this problem is maybe slightly simpler than text detection just for the reason that the aspect ratio of most pedestrians are pretty similar, and so we can just use a fixed aspect ratio for these rectangles that we're trying to find. So by aspect ratio, I mean the ratio between the height and the width of these rectangles. So they're all the same for different pedestrians, but for text detection, the height to width ratio is different for different lines of text. Although for pedestrian detection, the pedestrians can be different distances away from the camera, and so the height of these rectangles can be different depending on how far away they are, but the aspect ratio is the same. In order to build a pedestrian detection system, here's how you can go about it. Let's say that we decide to standardize on this sort of aspect ratio, 82 by 36. And we could have chosen some rounded number like 80 by 40 or something, but 82 by 36 seems to work. What we would do is then go out and collect a large training set of positive and negative examples. So here are examples of 82 by 36 image patches that do contain pedestrians, and here are examples of images that do not. On this slide, I've shown 12 positive examples with y equals 1 and 12 negative examples with y equals 0. In a more typical pedestrian detection application, we may have anywhere from 1,000 training examples up to maybe 10,000 training examples, or even more if you can get even larger training sets. And what you can do is then train a neural network or some other learning algorithm to take as input an image patch of dimension 82 by 36 and to classify y and to classify that image patch as either containing a pedestrian or not. So this gives you a way of applying supervised learning in order to take an image patch and determine whether or not a pedestrian appears in that image patch. Now, let's say we get a new image, a test set image like this, and we want to try to find the pedestrians that appear in this image. What we would do is start by taking a rectangular patch of this image, like that shown up here. So that's maybe an 82 by 36 patch of this image. And we'll run that image patch through our classifier to determine whether or not there is a pedestrian in that image patch. And hopefully our classifier will return y equals 0 for that patch since there's no pedestrian. Next, we then take that green rectangle and we slide it over a bit and then run that new image patch through our classifier to decide if there's a pedestrian there. And having done that, we then slide the window further to the right and run that patch through the classifier again. The amount by which you shift the rectangle over each time is a parameter that's sometimes called the step size of the parameter, sometimes also called the stride parameter. And if you step this over 1 pixel at a time, so if you use a step size or a stride of 1, that usually performs best, but is more computationally expensive. And so using a step size of maybe 4 pixels at a time or 8 pixels at a time or some large number of pixels might be more common since you're then moving the rectangle a little bit more each time. But so using this process, you continue stepping the rectangle over to the right a bit at a time and running each of these patches through the classifier until eventually, as you slide this window over the different locations in the image, first starting with the first row and then with further rows in the image, you would then run all of these different image patches at some step size or at some stride through your classifier. Now, that was a pretty small rectangle that would only detect pedestrians of one specific size. What we do next is then start to look at larger image patches. So now let's take larger image patches like those shown here and run those through the classifier as well. And by the way, when I say take a larger image patch, what I really mean is when you take an image patch like this, what you're really doing is taking that image patch and resizing it down to 82 by 36, say. So take this larger patch and resize it to be a smaller image, and then there's this smaller resized image that is what you would pass through your classifier to try to decide if there's a pedestrian in that patch. And finally, you could do this at even larger scales and run that sliding windows to the end. And after this whole process, hopefully your algorithm will detect what are the pedestrians that appear in this image. So that's how you train a supervised learning classifier and then use a sliding windows classifier or use a sliding windows detector in order to find pedestrians in an image. Let's now return to the text detection example and talk about that stage in our photo OCR pipeline, where our goal is to find the text regions in the image. Similar to pedestrian detection, we can come up with a labeled training set with positive examples and negative examples, with positive examples corresponding to regions where text appears. So instead of trying to detect pedestrians, we're now trying to detect text. And so the positive examples are going to be patches of images where there is text, and negative examples are going to be patches of images where there isn't text. Having trained this classifier, we can now apply it to a new image, maybe to a test set image. So here's the image that we've been using as an example. Now, let's say we run, for this example, I'm going to run a sliding windows classifier at just one fixed scale, just for purpose of illustration, meaning that I'm going to use just one rectangle size. But let's say I run my little sliding windows classifier on lots of little image patches like this, right, over. If I do that, what I end up with is a result like this, where the white regions show where my text detection system thinks it has found text. And so the axes of these two figures are the same. So there's a region up here corresponds to a region up here. And so the fact that this is black up here represents that the classifier does not think it's found any text up there. Whereas the fact that there's a lot of white stuff here, that reflects that the classifier thinks it's found a bunch of text over there on the image. What I've done on this image on the lower left is actually use white to show where the classifier thinks it has found text, and the different shades of gray correspond to the probability that was output by the classifier. So lighter shades of gray corresponds to where it thinks it might have found text, but where it's lower confidence. But and the bright white corresponds to where the classifier output a very high probability, estimated probability of there being text in that location. Now, for text detection, we aren't quite done yet, because what we actually want to do is draw rectangles around all the regions where there's text in the image. So we're going to take one more step, which is we're going to take the output of the classifier and apply to it what's called an expansion operator. So what that does is it takes this image here, and it takes each of the white blobs, takes each of the white regions, and it expands that white region. Mathematically, the way you implement that is, if you look at the image on the right, what we're doing to create the image on the right is, for every pixel, we're going to ask, is it within some distance of a white pixel in the left image? And so if a specific pixel is within, say, 5 pixels or 10 pixels of a white pixel in the leftmost image, then we'll also color that pixel white in the rightmost image. And so the effect of this is it'll take each of the white blobs in the leftmost image and it'll expand them a bit, so grow them a little bit by seeing what are the nearby pixels to the white pixels and then coloring those nearby pixels white as well. Finally, we're just about done. We can now look at this rightmost image and just look at the connected components, or look at the contiguous white regions and draw bounding boxes around them. And in particular, if we look at all the white regions, like this one, this one, this one, and so on, and if we use simple heuristic to rule out rectangles whose aspect ratios look funny, because we know that boxes around text should be much wider than they are tall. And so if we ignore the thin, tall blobs like this one and this one, and if we discard these ones because they're too tall and thin, and we then draw bounding rectangles around the ones whose aspect ratio, that is, whose height to width ratio looks right for text regions, then we can draw rectangles, the bounding boxes, around this text region, and that text region, corresponding to the Lulubee's Antique Mall logo, this Lulubee's, and this little open sign over there. This example, by the way, actually misses one piece of text. This is very hard to read, but there's actually one piece of text there that says Lulubee's again, corresponding to this, but the aspect ratio looked wrong, so we discarded that one. So, looks okay on this image, but in this particular example, the classifier actually missed one piece of text. It's very hard to read because there's a piece of text written against a transparent window. So that's text detection using sliding windows. And having found these rectangles with the text in it, we can now just cut out these image regions and then use later stages of the pipeline to try to read the text. Now, you recall that the second stage of the pipeline was character segmentation. So given an image like that shown on top, how do we segment out the individual characters in this image? So what we can do is, again, use a supervised learning algorithm with some set of positive and some set of negative examples. What we're going to do is look at an image patch and try to decide, is there a split between two characters right in the middle of that image patch? So for each of the positive examples, if you look at this first positive example, this image patch looks like the middle of it is indeed, the middle has splits between two characters. In the second example, again, this looks like a positive example because if I split two characters by putting a line right down the middle, it looks like a good thing to do. So these are positive examples where the middle of the image represents a gap or a split between two distinct characters. Whereas the negative examples, well, you don't want to split two characters right in the middle, you don't want to split two characters like that, and so these are negative examples because they don't represent the midpoint between two characters. So what we do is we would train a classifier, maybe using a neural network, maybe using a different learning algorithm, to try to classify between the positive and negative examples. Having trained such a classifier, we can then run this on this sort of text that our text detection system has pulled out. So we start by looking at that rectangle and we ask, gee, does it look like the middle of that green rectangle, does it look like the midpoint between two characters? And hopefully the classifier will say no. Then we slide the window over, and this is a one-dimensional sliding windows classifier because we're going to slide the window only in one straight line from left to right. There's no different rows here, there's only one row here. But now with the classifier in this position, we ask, well, should we split those two characters, or should we put a split right down the middle of this rectangle? And hopefully the classifier will output y equals 1, in which case we will decide to draw a line down there to try to split two characters. Then we slide the window over again, hopefully the class says don't put a split there, slide it over again, hopefully it says yes, do split a split there, and so on, and we slowly slide the classifier over to the right, and hopefully you'll classify this as another positive example, and so on, and we would slide this window over to the right, running the classifier on every step, and hopefully it'll tell us, what are the right locations to split these characters up into, to split this image up into individual characters. And so that's 1D sliding windows for character segmentation. So here's the overall photo OCR pipeline again. In this video, we talked about the text detection step, where we use sliding windows to detect the text, and we also use a one-dimensional sliding windows to do character segmentation, to segment out this text image into individual characters. And then the final step of the pipeline is the character classification step, and that step you might already be much more familiar with the earlier videos on supervised learning, where you can apply a standard supervised learning, again, maybe a neural network, maybe something else, in order to take as input an image like that and classify, which alphabet, or which of 26 characters A to Z, or maybe which of 36 characters if you have the numerical digits as well. But it'd be a multi-class classification problem where you take as input an image containing a character and decide what is the character that appears in that image. So that was the photo OCR pipeline, and how you can use ideas like sliding windows classifiers in order to put together these different components to develop a photo OCR system. In the next few videos, we'll keep on using the problem of photo OCR to explore some more interesting issues surrounding building an application like this.